The software-defined networking and OpenFlow webinar was made possible by the sponsorship of Big Switch Networks. Big Switch Networks are developing an SDN application for network virtualization, and you can get their open source SDN controller called Floodlight at the openflowhub.org. You can find Big Switch at bigswitch.com.
This webinar is just one of many vendor-independent data center and virtualization webinars available on IPSpace. To learn more about them, visit ipspace.net. And don't forget that you get immediate access to all of them with a yearly subscription.
Going back to my original diagram, what if the original diagram where I talked about routing protocols that populate the RIB populates the FIB, and the FIB decides what is the forwarding path for packets and frames. So what if instead of this, I had a central controller to update the FIBs on the routers and switches? What would that look like? Would that still be a network? Would it still be the sort of thing that you wanted to have? So just to recap, routing table is your routing information base. There are many routes for a destination in a RIB, but we only select the best route. We only load that one route into the FIB. And the FIB typically contains not only the input port, the output port, but often contains the layer 2 encapsulation data for the next hop, for those of you who are more network centric. So FIBs are built from RIBs in today's networking. In tomorrow's networking, it'll be different. To bring that back a little bit further, let's have a look at the device architecture again. The typical device architecture today is that the networking device contains the control plane, the forwarding plane, and the management plane all within itself. The software that runs the whole system today is reasonably complex. That is, software like OSPF, LDP, BGP is complex software. Multicast, sparse mode, dense mode, PM, PIM, all those protocols are all sitting inside of the software in an attempt to load data into the FIB for forwarding. And that means that today's networking devices are extraordinarily complex. A massive layer of control plane complexity resides around getting the right information into the FIB. So if instead of having everything sitting autonomously inside the system, we could have an OpenFlow idea, the OpenFlow model, and this is where we introduce OpenFlow. And that is that the OpenFlow controller sends the forwarding information data directly to an OpenFlow client in the device. The device firmware then loads that into the forwarding path. So now we've taken all that complexity around the things in the networking equipment, the OSPF, the BGP, the OSPF, the PIM, all that sort of stuff in this model. We'll come back to more practical details in a little while. The OpenFlow controller could load data directly to an OpenFlow client, which then loads it directly into the forwarding page. In this situation, there's really the only firmware or the only software in the device is chip firmware, enough to run the FIB or the TCAM memories, and to run simple device management functions. That is to present a CLI, to run the flash, to monitor the power, systems environmentals, and that type of stuff. All of the complexity around generating the forwarding table could be abstracted away to an external controller or layer. Now, it's also possible that a device could still maintain protocols and have OpenFlow support. So in a world where the complex software exists and runs spanning tree or OSPF, it doesn't have to replace this. So it's not like OpenFlow necessarily replaces all of that software that goes on in the network. OpenFlow could be in addition to. So that is, the RIB can still be loading data into the FIB, but so could OpenFlow be loading data into the FIB. And this is our transition strategy for the future. We'll talk more about the business impacts of this design in the later on section when we talk more about software-defined networking. But up until now, we've had a fairly if you've been following OpenFlow in the papers and in the industry, people have been more talking about the previous architecture. Now, I'll just go back a slide here. This here is very interesting to certain businesses where they want to have the dumbest possible device so they can have it for the cheapest possible price, because spending capital for them is bad. They only want to spend money in operational costs. This model is probably better for enterprise networks who have multifarious, far more widely flexible, creative. We've got different problems. The networking problems in a proper network which has multiple streams, multiple models, multiple flows, different protocols, uncontrolled environments to some extent. This system is probably the better answer, and probably is the way we'll see it in the future. So, the network operating system will change a little to handle all. We'll have the device operating system handling device operations: boot, flash, memory, TCAM chips, SNMP. SNMP will still be part of the future, I would say. At least that's the way it appears. You could consider a device to have no OSPF or multicast, and that device would have no code bloat. It would only have what you need. So the smallest code means less bug, less resources, less cost. Now, if you think about a typical device today, then how much money is spent to develop a product that has gigabytes of memory and flash, and it all has to load, and it all has to use the memory even when it's not needed. So even though your product X, you don't use multicast, that multicast feature is still there, it's still in the code base, and it could cause you a bug. And your CPU has to be big enough to handle it, because you might be the one customer in 1,000 who needs multicast, when in fact most people don't use multicast and never will. Or if they do, they use a vanishingly small component thereof. This is the exciting part for some companies, is we could just focus our network operating systems right down to something very, very limited. Let me take a sec to deviate off course a little bit here and challenge people who might not have thought too much about this. But is forwarding, which is what we're talking about, if a device that has a forwarding table that forwards Ethernet packets that have IP packets inside them, let me ask the question, is that a router or a switch? So we have typically today we have a 48 port switch with, say, 10 gigabit ports. Let's say it's got 32 10 gig ports and 4 40 gig ports, which is a fairly common merchant silicon device. You can buy these quite cheaply in the market for some few $1,000s a throw for a no-name brand. You can run an open source operating system on them. Is that a router or a switch? Well, if it's just forwarding packets, it might not be either, right? So let's have a look at this a little bit further. In a normal networking device, so in what we would call traditional, or it's not legacy yet perhaps, a frame would be received on operation number 1. It would hit VLAN 10. In the second step of the operation, we would look up the destination MAC address of an Ethernet port and decide which output it would go. So we would know, for example, that in step 2 that MAC address maps to going up the trunk port. So in step 3 we would then add the VLAN tag as it egresses that port. And when received on the trunk port, the VLAN tag is then marked, and then it's forwarded into the table which looks up the VLAN and the destination address. It's step 5, and then dispatched out VLAN 10 at the port 3. So the frame is received by an input process. The destination address is looked up in the forwarding table. The forwarding entry age is checked, that the output interface is checked to make sure it's still within the time, and the output interface is still up and valid, and then it's dispatched after the frame is checksummed with a CRC to the neighboring switch. That, for a nominal 2-switch connection, is a 2-port arrangement. In a network which is only forwarding on FIB, now this assumes that you have a pure FIB environment, that you have no external data handling things, then you really only have 2 phases. the packet would be received and the lookup against the forwarding table would be matched. There's no VLAN tagging here because all of the flows are, it will always match an entry in the fib. So the OpenFlow table is consulted, the fib is handled, and it would be dispatched out of port 4. And then on the neighboring switch, it would be received. Wouldn't necessarily be VLAN tagged. And then a second OpenFlow table lookup is done, and the output port is determined. I call this flow forwarding. So to come back to my original question on to routing and switching, I regard switching as forwarding by destination MAC address, because really that's what we do to perform a switch today by traditional means. So if I'm forwarding by MAC address, then I'm switching. If I'm making the forwarding decision by IP address, that is at layer 3, for those of you who track that information, then I am routing. If I am forwarding the data by flow, then I call this flow forwarding. And that is the difference that I've decided to go with. It's largely arbitrary, and you could make this any way you like, but today I use this syntax to separate the two. So if I am switching, if I'm forwarding Ethernet frames, then I am switching because I'm forwarding by destination MAC. If I am routing or layer 3 forwarding, then I'm doing it by destination IP. But flow forwarding means I'm doing it by flow rule. And to be Ivan about it a little bit, I just wanted to talk about switching versus bridging because it's really important. Switching, to a large extent, still includes layer 2 switching, layer 3 switching, or layer 4 switching. Again, it just talks about, I prefer to use the term routing is forwarding by IP. But routing can also be called layer 3 switching because what you're actually doing is just consulting the layer 3 heading to go forward. I don't agree with Ivan on this particular point, but he found it was important that I put this slide in. So there you go, Ivan. I put it in for you. So what I want to do now is very briefly talk about OpenFlow controllers. We talked earlier about, how the fibs would get into the database. So this is a brief introduction to what a controller is. So if I have a controller that is producing the data that puts data into the fib table of a network device, then it's a piece of software. It's an application. It's a software program that sits on some computer somewhere. It could be an appliance, it could be a VM, it could be wherever it is. The controller has to have connectivity to all network devices so that it can send the fib updates to all of the devices, and it would also need to receive back any data from the devices. The controller would build a topology of the network in memory and run an algorithm that would decide what the forwarding table would look like. Once the algorithm has been executed across the network topology, then it would dispatch updates to the forwarding tables using OpenFlow, and that is OpenFlow. OpenFlow is an API and a protocol which decides how to map the forwarding information base entries, the fib entries, out from the controller to the device. In this sense, a controller is, if we look back at what we know today and what we understand about the networks, a controller has some similarities to a stack master. So anybody who has used a stack of switches, so for example, if you have 5 switches in a stack, then one of them will become the stack master. And the way a stack master works in a stack of switches is the stack master is the one that takes all of the data about the forwarding table. It's the one that runs the spanning tree calculation and says these are the forward inputs, these are the outputs. And then what it does is it decides what the forwarding table looks like and then sends those entries down over the stacking backplane to each of the devices so that it's each got a local forwarding table. The fib of each of the stack members is determined by the stack master. And something similar also happens inside of Cisco Catalyst switches where the supervisors sit in the center of the network. They actually decide all of the forwarding information for the entire chassis from the routing protocols or from the spanning tree or from the whatever. And then when it's done, it actually then outloads that to each line card. The line card then has a local forwarding engine. So if the supervisor can do that, then that is what we are achieving with a controller. So in this slide, what I'm discussing is there are 5 elements fundamentally that you need to be thinking about. One is at the bottom there, you've got the network. Then you have the OpenFlow protocol, which communicates to from the controller. The controller has its own model of the network, and then it presents a user interface out to the user so that configuration data can be come in. Let me run that from top to bottom because it's worth just emphasizing this. This is the difference between this network or other networks. The user interface presents something to the user. The user then says, I want to select these rules or these processes. I want to configure it this way or that way. The controller then looks at its model of the network, which it's built by gathering information from the network one way or the other. More on that later. And then says, I need to program the forwarding tables in all the network devices like this to be able to achieve that successful outcome. The OpenFlow protocol is a protocol. It's not a software, it's not a platform, it's a defined information style that allows for dynamic configuration of the networking devices. And we'll talk more about that. Okay, so just to ruminate about this and to sort of expound on what this might mean, a controller could build a model of the network and have a database of what it is and then run an SPF algorithm across it to produce the same pathing as OSPF. Because if you consider how the OSPF protocol works today, basically it builds a database inside of it by receiving updates from all of its neighbors about the configuration, and then it runs the SPF algorithm over the LSA database. What if you just built a model in the controller and then ran an SPF algorithm over it and then loaded down some tables to that? Then we could certainly do that. Now, I could also run the controller with BGP as a BGP peer, and it would have a model of the network, and it would then from the BGP table decide how to interoperate with external networks. Right? This means that BGP would run mostly as a root server type concept, but it could just be a single hop BGP peer. And this is a very popular implementation, a lot of research being done in this area. So it will probably look to replace interesting things. Okay, I wanted to sort of hold there for a second. So what we've done is talked a little bit about how a controller and an OpenFlow and the networking device works and how it passes information into the forwarding database.
To get more information about IPSpace webinars, please visit ipspace.net.